To a surfer, a wave on the ocean is an inviting form of energy. How do waves form, and where do they develop?
My definition of a wave, it's a moving palette of ocean energy that invites us as humans to ride along and participate in that movement, that flow of energy.
Scientists wouldn't disagree entirely. Waves are vertical expressions of energy. Waves begin far out at sea, where they're whipped up by the wind. These swells carry energy from the wind across the surface water all the way to the beach. Surfers can ride waves because as the waves roll ashore, they climb. In shallow water, wavelength decreases. The bottom of the wave drags on the sea floor and the crest of the wave rises, moving along until it breaks. Changes in ocean levels are caused by tides. Tides rise and fall with the gravitational tug of the moon and the sun. The effects of the moon's gravity is the stronger of the two. The effect changes as the moon rotates around the Earth. Physicist James Treffill explains.
When you have this situation of the moon pulling on this side and then pulling the Earth away from the ocean on the other side, it looks like you've got a bulge where the ocean is sort of football-shaped and the Earth is baseball-shaped inside. And then that moves around the Earth and follows the moon.
Twice a day, tides rise and fall, and waves constantly lap our shores. Over time, waves can change the shape of our coastlines and create new beaches. Maybe the surfers have it right after all.
Riding a wave it's dancing with the ocean's pulse, with its mystery. It's like playing music with the ocean. Okay, so today we're talking about the ocean and waves and tides in particular. And you just saw there kind of the whole brunt of the entire lecture today, which is about how waves form, what they do, how tides happen, and we're also going to talk about the circulation of water in the oceans as we go. So let's dive in here. This is a photo I actually took last time I was the only time I was ever visiting Mexico. I was on the coast down in Tulum. And these waves were just coming in, some nice little waves over the ocean, and these humongous like clouds building in the background. It was just before a storm came in and hit. It's pretty cool. So let's dive into this. Ocean currents. So there's different types of ocean currents. We're going to talk about what are called surface currents, and we're going to talk about currents that move more vertically in the water. And the whole situation kind of looks an awful lot like a conveyor belt if you could see all the parts to it. But first, surface currents. These move horizontally along Earth's upper ocean surface. The reason that surface currents flow is because wind blows across the surface of the ocean where there's a large stretch of water, and the friction of the wind against the ocean's surface causes waves to start to build. That's why large bodies of water, like the Great Lakes, which are kind of like freshwater oceans, can get some huge waves, waves that are big enough that you can even surf on them. But you need a large body of water for the wind to pick up enough speed going across it to make the friction that's required on the surface to move get the wave action actually going. So surface currents, waves caused by the friction of the ocean surface with the wind. Okay, we could kind of keep tracing that back if we wanted to, and talk about how the differential heating of the Earth's surface because of the sun is really what drives the pressure systems, and we'll talk more about this in the weather unit, that moves the wind. But it is the wind itself that is actually causing the waves that you might see on the ocean, or the waves you'll see on a large lake. That's the cause of it. Now, what do ocean surface currents look like? So the surface currents actually look quite different depending on if you're in the northern or the southern hemisphere. So for us, if you look at my map here, you can notice in particular the peninsula of Florida sticking out there. That will kind of orient you to where you're at. To the right of the peninsula of Florida there is what's known as the North Atlantic Gyre. And so if you notice that one and you kind of keep looking across, you're going to notice some smaller ones and some other kind of large ones there. The North Pacific Gyre is quite large. And if you look at the direction those are going, they're all spinning in a clockwise fashion. Notice that? Now look down towards the southern hemisphere. Look, say, between Africa and South America, and you'll see the South Atlantic Gyre. Notice how that's rotating in a counterclockwise manner. So that's caused by something called the Coriolis Effect. And I'll put up a slide here with that described on it here in a second. But the reason that the ocean currents rotate in different directions is because the Earth rotates on its axis. So the Earth's rotation causes the direction the wind is blowing to kind of get deflected and curve. And so this is also why our weather systems rotate clockwise in the northern hemisphere and counterclockwise in the southern hemisphere, which you might have heard something called a cyclone and an anticyclone. That's the same thing. So the water surface patterns kind of mimic the wind patterns as well. But yeah, they are bounded by the continents, and so the continents kind of like make little catch basins in which these gyres spin in, that they rotate. But this is the surface water, not the deep water, okay? And it's caused by the wind, and more importantly, the rotation is caused by what we call the Coriolis effect. So let's kind of go ahead and define that. So these gyres are these large circular moving current systems that dominate the surfaces of our oceans. And the Coriolis effect is the cause for this. And like I said before, it's because the Earth is rotating on its axis that wind gets deflected, and therefore the currents in the water also get deflected. So if you kind of pictured wind moving straight across the surface of our northern hemisphere, if the Earth rotates underneath of that, it gives it the appearance and actually the real effect of it turning and rotating. It's in many ways, you could experience this on if you had an old-fashioned Ferris wheel or yeah, that's right, a merry-go-round, that's what I'm trying to say. So if you've ever been to a park, maybe they got rid of those because they were unsafe, but in the old days, we used to have merry-go-rounds, and you get it going really, really fast and try and hold on to the thing, right? You might be sitting on it while everybody's spinning it. If you were to try to roll a ball across that from the center outwards while it's rotating quickly around, the course of the ball would be straight, but it would appear to curve because the merry-go-round rotates underneath of it. So the Earth is kind of like rotating underneath of the wind and the water, and that's what makes it appear to curve. And it's a real effect for us, like these things rotate, right? Okay, enough about that. So the climate has a lot to do as well with the surface circulation. Okay, so when the currents from the low latitude regions move up into the higher latitudes, heat is brought from the equator up towards the poles. Okay, so there's like this heat transfer system that the Earth actually has kind of built in because of these rotating currents. we rotate the warmer water from the equator on up towards the poles. Okay, and then the colder water at the poles moves downwards. So what the effect that this has is it actually creates kind of a moderating effect on any land masses that happen to be kind of the recipients of that warm water moving upwards. And you can see this really clearly along our eastern coast in the United States. It's a little hard to see this picture, but if you look on the left side there, that's the outline of our eastern coast, and you can see Florida down there. The red is the false color image of the hot water because it's rotating and it's moving up the coast. So imagine if you live, say, in the Carolinas, okay, or Atlanta, like on the coast of up there by Georgia, like up that direction, you're going to have these warmer currents moving up, and that warms your air mass a little bit too. So those cities and those towns that are living on the coast there experience like a kind of a warmer climate than they would have experienced if that wasn't there. It would be much colder. So you could actually have, like, say, the same latitude as Indiana, but have less hot summers and less cold winters than we do because you're on the coast there and this warm water is kind of pushing its way upwards like that. You can kind of see where it meets the cold water up there. Okay, so let's talk about the other type of ocean circulation. We've got all this stuff moving around on the surface, but we also have motion vertically through the water, and this is known as upwelling. So what happens, so the cold water that's deeper under the ocean can replace the warmer surface ocean water. So upwelling what happens is it brings all these nutrients that are down there in the deep ocean right up towards the surface. Well, all that phytoplankton and all the little organisms that need that stuff to survive are dependent on these circulating currents, where the colder water that's deep underneath, say, the equator, rises up and meets the surface. It brings all these nutrients. And the whole flow of this system, it's kind of like this conveyor belt where you've got water that's near the poles that's sinking because it is, cold, and it flows along the surface of the bottom of the ocean, and then it rises up again at the equator as it starts to warm back up. So this has a huge effect on the life that can live in our oceans. And this is looking at the coast here of Africa, where there is some upwelling going on. It's got a picture of the surface current there, but the water is coming up from deep, and it's got lots of nutrients in it, so that all those phosphates and things that everything needs is welling up to the surface. So you have this huge growth of plankton and phytoplankton, which need sunlight and need nutrients. They're basically like little single-celled ocean plants, if you will, kind of. You could think of them that way. But they're making a lot of our oxygen. So this whole system is kind of drastically important, not just to our climate and our temperature, but it's also like important to just life in general, because without it, we don't have the oxygen we need to survive. And without it, the base of the ocean food chain, which is these little plankton, if you don't have those, the whole ocean collapses. Like, there's no fish, there's no whales, they're like right on up, and believe me, that's going to affect people. So one of the things we'll talk about later on in this course is climate change, and our climate is most certainly changing. And one of the possible scenarios of tragedies that could come out of that would be for these deep ocean currents to get cut off, for them to stop. And if that happened, we'd be looking at a huge tragedy. I mean, like, global scale event that would be very, very dangerous to all life on the planet. And we'll talk more about that in the climate unit, but believe me, these ocean currents and climate are deeply interconnected, which is one of the reasons why people have a hard time understanding climate science, because it's not just an isolated thing. You have to take into account not only the wind and the weather and the overall temperatures in different places on the planet, but you have to really take into account ocean temperatures and ocean circulation. Okay, enough about that. So let's continue here with this deep ocean circulation. So these things are known as density currents, and they're vertical currents in the ocean water that are really the result of differences in density. I'm sure you've probably heard that if you go to the ocean and you lay down in the water, you can float considerably higher in the water in the ocean than you would, say, in Lake Superior, right, in a freshwater body of water. And that's due to density differences. The denser water is going to sink deeper, and it's going to cause things that are less than dense than it, like maybe you, to float upwards. So if you ever have the opportunity to, say, go to the Great Salt Lake, I've actually been there. It's kind of gross. It's out in Utah. It's very, very salty. It's so salty that in places the water looks white on the edges, and there's crystals of salt forming on the sides of the water on the banks. But you can wade out into that. I tried. I couldn't get far enough out that I was comfortable laying down because it was mud up to my kneecaps. But you could wade out into that and lay down on your back, and you would float way high out of the water because there's so much salt in it. So a tiny change in saltwater salinity, a little bit more saline, a little bit more salt, and the water becomes increasingly more dense. Saltier water will sink easier than less salty water. The same thing with temperature. Right? Colder water is more dense than hot water. Kind of like, think of a hot air balloon rises up, right? It's the exact same thing. So colder water, more dense. Salty water, more dense. Both of those situations occur at our poles. So it's colder, it's a little bit saltier, and it sinks. Okay? Near the equator, you have the reverse of that happening. So this whole situation kind of acts as this big conveyor belt sort of a thing. Like I said here, the system kind of starts up there in the high latitudes because of the density differences. So you get increased ocean salinity because of all the evaporation, okay? And then this stuff it's more salty, it's getting colder, and it's going to sink, okay? And then the whole system starts to act like a conveyor belt. And that's really, I mean, it's a way oversimplified model of this, but you kind of have to do that so you can understand it. So you have these currents that are traveling from the poles downwards, vertically through the water, along the bottom of the ocean, okay, carrying with them all sorts of nutrients and things, and then rising up again near the equators where they bring all those nutrients back to the surface. Here's a sort of a really generalized picture model to show you kind of what that looks like. I'll give you a second here to take it in. So let's just focus on North America up there, okay? So you've got surface flow, which is the warm water there. It's in red, and it gets up there to the poles, and then it sinks, okay? Where it sinks, it's going along kind of the bottom of the ocean, flowing back towards the equator, and then we also have this kind of cold subsurface flow. It's a bit more complex than I'm trying to kind of make in it here, but it flows along the surface of the ocean, and then we're going to see it rise again over there in the Pacific, and then move back along the surface. So you get these weird, like, sort of a conveyor system. It's a little bit different than the Coriolis spinning gyres that are happening on the surface water. Okay, so looking at that underwater, it is quite complex, but you can see that, generally speaking, the far northern, far southern latitudes, the north-south pole, we've got water sinking, moving along the bottom, and then, of course, rising back up again near the equator. Okay, that's in a real general sense, that's kind of how it works. So let's talk wave characteristics now. I'm sure many of you have experienced a wave, whether it was on, even Lake Monroe or one of the other smaller lakes here around Columbus. If you've been to the ocean, you definitely know what a wave looks like. But ocean waves, we can describe them based on some of their characteristics. Okay, remember, these are caused by the wind is what causes these waves. Okay, so wave height is the vertical distance of the wave, like how you could almost kind of think of it on how tall it is from the very bottommost part of the wave all the way up to the crest, the highest point. Okay, wave length is the distance between any two points onto two separate waves. So like you could go from the crest to the crest, and that would be the wavelength. Okay. The wave period is the time it takes for one full wave, one wavelength, to pass a position. You usually measure that in wavelengths per second. Okay, so how many waves can pass by a point in a given second? And then we'd refer to that as the frequency. So the wave period, if you were, say, a buoy sitting out in the ocean, and we started counting, 1, 2, 3, how many waves can go by the buoy in a fixed amount of time? Okay, so you could have really small waves moving very quickly. You could have small waves moving slowly. You could have big waves moving very slowly across the ocean, right? The last word up here is fetch, which is an important word. I think I've used it already. Is the distance that wind travels across the open water. The wave fetch is really what determines how big your waves will get. So if you're a surfer, you know intrinsically that you can surf in the ocean. The ocean is humongous. It's most of our planet, right? So the wind has a long, long way to travel across the ocean. Waves can get gimongous. You know that occasionally you can surf in really large lakes like Lake Superior. There's some spots you can surf where the wind has a long fetch. There's a huge lake, and the waves occasionally build up big enough that you can get on them with a board. However, you wouldn't go down to, say, even Lake Monroe and sit there and wait for some waves, right? That would be dumb, because they're never going to get big enough, right? Because there's just not enough distance before the wind runs into a shoreline for it to get that big. Now, they can get scary, for sure, but they're not going to get super, super huge. Okay, so let's look at the anatomy of a wave. If we actually break down what a wave looks like, what are the particles doing underneath the water? It's kind of interesting. If you've played in a wave before on the side of a beach, you know that it can kind of pick you up and throw you into the ground and drag you across the sand and then deposit you back on the beach. Well, what's going on there? Well, as a wave moves through the water, the individual water particles, like if we were to put little bits of stuff down there underwater and watch what they're doing, they don't actually move forwards. What they actually do is make a neat little circle, which is what gives the wave its kind of apparent rounded part at the top when you're out in the open water watching one of these waves. So going downwards from the top of the wave, the little circles that the particles make get smaller and smaller and smaller. And if you ever put on a mask and get underwater and watch a wave as it stirs the sediment up on the bottom of the water, the sand, you'll see it kind of lift up, curve around, and then fall back down. Okay? So this is also the reason that if you threw a bottle, like with a message in it, out in the open ocean, and the waves were passing underneath of it, the bottle is honestly just going to bob up and down and not go anywhere. The only way that bottle's going someplace is when the wind itself is hitting the bottle's surface. It will start moving it in one direction or another for the most part. But an individual wave's not really going to carry your water, your message in the bottle, because while the wave itself moves forward, the water itself is making a little circle and staying put. Okay, now what does that look like when it gets to the beach? It looks quite different when it gets to the beach, but this is the reason you're going to see a wave crest on the beach. Okay, now this is just explaining what I just said to you there. It's the wave motion is circular. Okay, the energy moves forward. Okay, but the individual water particles, they just make little circles. Okay, or bigger circles if it's up or towards the top part of the wave, the larger part near the crest. Okay, let's talk about breakers here. What surfers are interested in. Waves break, as you might know, when they hit shore or when they hit a break line off the coast, off the shore just a little bit. And if you've ever been in a large body of water and walked out and found a sandbar just offshore a good ways, that's a break. And you'll notice that waves will be breaking on that, and then they'll kind of stop breaking again and then head in towards shore, and then when they hit shore, they'll break once again. So what I'm talking about by breaking is when the wave lifts up and crashes over itself. It doesn't look rounded anymore. Like it looks like somebody cut a C out of it. The reason that waves break is because that little circular motion that you're seeing that we drew there, As it reaches shore, there's friction, and the bottom part of the wave actually slows down, and that causes the top part of the wave, which is continuing forward at a faster speed, to crash over top of the bottom part of the wave. And also, because the bottom part of the shoreline is sloped, the wave gets lifted, it gets pushed up. So you're watching all these waves come in toward shore. They look like kind of nice and not super menacing. And then just as they hit as the bottom of the wave touches the ground, the wave lifts up, gets taller, curves over, and crashes. And that's the surf zone. Right? That's where the breakers are. The bottom of the wave decreases in velocity. The top's still going quite fast, and it curves over and crashes. There you go. So I wanted to show you, just how impressive waves can get. And I've experienced some huge waves in my life. In fact, one time I had the opportunity to actually surf during a hurricane, and it was, I can tell you, it is the most scared I've ever been in my entire life in the ocean. There was a hurricane coming in off the coast of Delaware, and I happened to know some people who had surfboards, and I wasn't really much of a surfer myself, but I really wanted to get out there and give it a shot, and I got 2 runs in all day. 2 times, like all day, made it 2 times. Now, they were evacuating the entire coast of Delaware at this time because a humongous hurricane was coming in. I think it was Hurricane Felix, if I remember right. I'll never forget this. These waves were so big because the wind was so powerful across the ocean. They were lifting up so high, they were cutting 10-foot banks out of the side of where the sand used to be on the coast. Like it was just a cliff. We had to slide down this thing with our surfboards. And then trying to paddle out into that with these waves just demolishing you, it was next to impossible to get out to where the waves were not breaking. You had to duck dive. You had to, as the waves started to break, you had to hold your breath and push your board and yourself underneath the wave, and then hope you could stay under long enough for the wave to pass overhead, and then come back to the surface and just keep paddling as hard as you could. But once you got out there in the pictures, you can see to where the waves are not cresting, you just bob up and down. And these waves were so huge that I was trying to surf, probably a better way to say it, that as I bobbed up to the crest of the wave, I could see like all the waves breaking on shore and everything happening like far away. I could see people lined up on the highway during the evacuation watching us surf out there. And then the wave would dip down into the bottom of the wave, and I could see nothing. Just a wave in front of me, a wave behind me. I mean, these things were easily over 10 feet tall. They were humongous. It was terrifying. And then you start paddling like mad, and you want to stand up just as that wave is starting to crest, because it's going to start pushing you forwards. You're not going to bob up and down anymore. The water's cresting over on itself. It's going to bring you forward, and then you drop in. So on a surfboard, dropping in, you're up on the crest of the wave, and you lean forwards, and you fall down the front of the wave as the wave's pushing you forward. So there's just this crazy microphone fell off there. There's this crazy amount of energy moving forwards that you're on, and you try to ride that thing out. And boy, I got eaten up that day. It was pretty terrifying. I remember being on the bottom of the ocean with my face getting scrubbed back and forth in the sand, back and forth, and thinking I wasn't going to be able to make it back up to the surface, just getting a little bit of a breath before the next wave came down on top of me and then just flattened me to the ground again. And you can't see anything. You don't know where you are. This is pretty terrifying. But waves are something else, man. Let me tell you what. Here is a video that I dug up of somebody surfing one of the largest waves. And I don't know if this is still the record holder, but this is one of the big wave surfing is something else. These are much bigger than the waves I was just talking about. These are some humongous waves that this guy is surfing. You actually have to be towed in on a jet ski to get onto the wave, because you can't paddle fast enough to catch these waves. And they're so choppy that you have straps on your surfboard, and you strap your feet down so you don't get knocked off your board trying to ride these things. So let's check this out here.
The only time it felt big is when I was kicking out and the white water hit me and it felt like a ton of bricks. And it was just a teeny little white water.
My name is Garrett McNamara. I'm from Hawaii. I'm here in Europe, off the coast of Portugal, in a little town called Nazaré. It's the only place in the world that I know about that has rogue waves on the beach. The rogue waves are created from this 1,000-foot deep canyon that runs all the way to the shore. The waves were not supposed to be that big this day. Because they're rogue waves, swell comes from one direction, hits the canyon, comes down the canyon, and goes across a sandbar, and they all meet at one point and create a rogue wave. As I rode this wave, it seemed pretty massive, but I couldn't quite tell how big it was. When I got to the bottom and turned and got around the wave and went to kick out, it landed on me. It felt like a ton of bricks, probably one of the most powerful waves I've ever had land on me at the shoulder. And it was pretty amazing.
Yeah, so that's something else there, isn't it? I mean, he was talking about rogue waves, which are formed a little bit differently, but yeah, still similar. You've got wind blowing the surface of the water, right? And there's some other effects there that he was talking about, the shape of the underlying area of the ocean there, and how that causes the waves to confluence and come together and get really, really huge. But yeah, wow. That was something else. Those were some humongous waves there. So anyway, a couple last things to talk about here. Sorry I get sidetracked because love talking about waves and surfing. But tides. So you might be aware that the Earth, anywhere on the surface of the Earth for the most part, if you're by the ocean, you're going to experience 2 high tides and 2 low tides a day. So why does that happen? Well, the causes of our ocean tides is essentially gravity. And it's the gravitational attraction between the Earth and the Moon for the most part. The Sun does play a role too as well, which we'll see here in a second. But the bigger force is the Moon. So Earth, Moon, and Sun interaction causes the gravitational forces cause the water to swell up on the sides of our planet. The Moon's gravity is pulling on the Earth and the Earth on the Moon, and because the water on our planet isn't attached to anything, it can get lifted up very easily. The ground itself actually rises ever so slightly as well. That's how powerful the gravitational forces are between Earth and Moon. But the water, obviously, it can move very, very easily, and it does. It bulges out towards the Moon and away from the Moon. What does that look like? Let's take a look here. Here's a photo showing you what's going on here. Now, let me try and describe this to you and explain it a little bit. So the arrow there is pointing towards where the Moon would be. Okay, and the Earth rotates on its axis, right? That's what gives us day and night. Okay, forget about the Moon's motion for a moment. Just focus, or even the Earth's motion around the Sun. Just focus on the fact that the Earth spins on its axis, right? As we go towards the eastern side of our planet, we see the Sun come up. As we continue around, the Sun dips in our west. Okay, so if you put the Moon over there to the right of this picture, what's going to happen is all the water on the planet is going to pull towards the Moon, which makes a very, very high bulge of water. And then what occurs is the Earth rotates underneath of that. So what's happening along the coast of Florida, say, or is going to happen, is the Earth's going to continue to rotate, and if you're standing on the coast, you're going to see the water rise. Okay, and that's going to be high tide. And when you go through high tide, you're going to be in low tide. Okay, now there's an additional effect here. Okay, on the opposite side of the Earth, opposite to the Moon, another bulge occurs. It's a little difficult to explain this bulge. They tried to a bit in the introduction, but you could kind of think of it as sort of like 2 effects occurring. First of all, the Earth is getting squished top to bottom. So think of the water getting squished top to bottom. It's going to ooze out the sides. Okay. Secondly, the Moon is tugging very strongly on that front side of the Earth that's facing it. The opposite side is not as experiencing as much of a pull as the front side of the Earth is that's facing the Moon. So all those forces together equal a bulge on the opposite side, so that there's two bulges. So since 24 hours you go all the way around the Earth back to where you started again, you're going to pass through bulge, low tide, bulge, high tide, low tide, and then that's 24 hours, you're back around again to going through both bulges again. So that's why you get two high tides, two low tides, pretty much everywhere you are on the planet. Now there's another effect that can cause a really, really high tide or a really, really low tide. Okay, so these are known as spring tides and neap tides. And the way this occurs is that you can get the highest high tide during a spring tide. And what's occurring there is there's an alignment of both Earth, Moon, and Sun. So not only are we feeling the Moon, but we're feeling the Sun lined up with all those forces right in line together. And that will give us the highest high tides that we could get on the planet. Okay, it's also going to give us the lowest low tides. Okay, because if you get the highest high tides, you also have the lowest low tides. Now the neap tides are when you kind of have the tides don't fluctuate as much. And the reason for that is because you end up with the Earth, Moon, and Sun at a right angle to each other. Let me show you a picture and it will make sense. But for the quiz, all you need to know is that spring tides will give you the highest high tides and the lowest low tides. So here's a picture that you see here. If you've got Sun in the first picture on the left, if Sun is to the right and the Moon is either where it's at on the right side of the picture or on the left side of the picture, in other words, it goes Moon, Earth, Sun, or Earth, Moon, Sun, either one of those gives you a spring tide. Okay, it makes the biggest high tide you can have and the lowest low tides. If you have the Moon at a right angle in first or third quarter, which we haven't talked about yet, so you've got Moon above or Moon below Earth, Earth in the middle, and then the Sun to the far right or the Sun to the far, well, I guess if we're going around, it's going to be to the right. So you're going to have what we call a neap tide, which kind of levels everything out because you got the Moon pulling one way, you got the Sun pulling the other way, so everything kind of levels out a little bit. Anyway, that's everything to do with waves and tides and the wind, Coriolis effect. I think we can wrap her up there. Go ahead and take your quiz.